pictures. So what do zebra stripes, right, on the left-hand side, and the subframe. So if you blow eye subframe, okay, what do they in common? What can we? These are completely different pictures, okay? Right. So look at the zebra stripes. So you see black color and white color, and then you see some kind of interface in between. Okay, so this is the zebra stripes, and subframe. So you blow a bubble, and you see some kind of subframe, some kind of shape, right? So this, for example, this you see some kind of a sphere, right? Some or this, okay. This is some shape between, okay, two parallel planes. So what do what do these two pictures in common? Okay, zebra bright stripes and subframes. So, and the answer is zebra bright stripes and subframes can all be described mathematically by the so-called Allen-Cahn equation, which I'm going to study today. So what is the Allen-Cahn equation? It's very simple. It's okay. I hope after my talk you can remember this equation at least. So left-hand side is the Laplace operator, the well-known Laplace operator, and the right-hand side is some nonlinearity, which is u minus u cube. So this is the graph of u minus u cube. So you have two zeros, three zeros, minus 1, 0, and 1. Okay, and it goes from plus, and so change sign and come. So this kind of bistable nonlinearity, right? So this is this is the equation we are going to study today. Okay, this is called the Allen-Cahn equation. So what is the Allen-Cahn equation? So the Allen-Cahn equation can be considered as the Euler-Lagrange equation of this so-called Ginzburg-Landau function. Okay, so the first term is the kinetic energy with the diffusion energy, and the second term is the most important term, is the so-called double wall potential. So why is it called double wall potential? Because the second term, you see you have two zeros, right? Minus 1 and 1. Okay. And if u not equal to minus 1 plus 1, then this is strictly positive. So this is called double wall potential. This means we have two zeros, and except these two zeros and the w is positive. So this is called double wall potential. And so what does these two faces mean? The minus 1 and plus 1. So minus 1 and the plus 1, they represent two faces. So for example, think about the zebra stripes. So minus 1 may correspond to the dark color, and the plus 1 may correspond to the white color. Okay, so these are the two faces. Okay, so now if we don't have this kinetic term, then the only solution will be plus or minus 1, right? Okay, so now, however, the gradient term, this gradient term penalizes the sharp transition between the faces. So you cannot have a sharp transition from minus 1 to plus 1. You must have something in between, and because this is the kinetic term. Okay, so this is called a phase transition. This is called phase transition. So this is the equation that's a very important equation. It's like a fundamental equation for phase transition and shift conductivity and mathematical biology. Okay, which models the zebra stripes and the image processing, and even now big data. Okay, data science. You can also use this Allen-Cahn equation to model the data science. So, and one of the topic I'm going to discuss today is the deep connection between of this problem and minimum surface, right? Which is the minimum surface which models the so-called subframes. So subframe, the surface of the subframe are nothing but minimum surface. So that's why the zebra stripes and the subframes, they are connected by this Allen-Cahn equation. Okay, so I explained the quiz and the answer. Okay. So this equation models so-called phase transition. So phase transition means so you on most of part your solution is like -1 and +1, but then there's an interface in between. So we want to study what is this interface. What is this interface? So and mathematically, this is called the e-Bernstein problem. So if we put a e-Bernstein in front of Laplace, put a 1 over e-Bernstein in front of the nonlinearity, so that e-Bernstein is like measures the length of the sharp interface. And so, and this is related to called minimum surface theory. And so if U is a local minimizer, then it has been proved, okay, this 40 years ago, that the interface, the nodal set, okay, approaches to minimum surface. So this problem is called the e-Bernstein problem because Bernstein problem is about the minimum surface. So this problem is like a perturbation of the Bernstein problem. So the connection between the Allen-Cahn equation and the Bernstein problem has been studied long time ago, like Modica Motorola in the 70s by gamma convergence, and Kwong and Steinberg in gamma convergence in 89, and Caffarelli and Cordova, they prove sigma alpha estimates, okay, for interfaces. And also Hutchison and Tanagara gave quantization of the energy, and Tanagara and Wakara Masakura and proved the sigma alpha estimates for stable solutions. And with KD1, which I'm going to mention later, this we obtain the C2 alpha estimate. So this is such a simple problem. Is related to the minimum surface, and recently there's a renewed interest in building the so-called minimax theory of Allen-Cahn and the corresponding in the minimum surface. So for example, in 2018, Goraco developed the minimax theory for Allen-Cahn equation in analog to the minimax embedded minimum theory by Marcus and Levis in 2017. And Gasper and Goraco also prove a so-called wire law for the density of minimum interfaces, and which is in analog to a wire law for a volume spectrum by Niko Movich and Marcus and Levis in 2018. And Chordish and Martinidis in 2019, they use Allen-Cahn equation to prove the so-called multiplicity 1 conjecture of a minimum surface by Marcus and Levis in R3. So there's a huge interest between the Allen-Cahn equation, the people study Allen-Cahn equation, and the geometry side, the minimum surface side. So what I'm going to talk about today, I'm going to concentrate on the Allen-Cahn equation side. And so the aim of my talk today is a classification of solution. I wanted to say, what are the possible solutions to this simple looking problem. So we want to use the property of U to simplify the solutions, so reduce the complexity of the nonlinear equations. So you may wonder why do you study this? Why do you study this classification problem? Let me give you some motivation. So a fundamental problem in nonlinear partial differential equations is the classification of solutions of PDE. So the simplest example may be the Laplace equation, the so-called harmonic functions, and these harmonic functions, this has been classified. Okay, there are many examples of harmonic functions. For example, x² minus y², xy, and e to the. For example, this is just in 2D, right? In 2 dimensions. And the question is, how do we classify all these harmonic functions? Right? So in 1800, Newell proved a very fundamental theorem. It says all bounded harmonic functions are constant. So this may be the first classification of harmonic functions. Right? So a more general Newell type theorem, which is proved, I think in the last 40 years, or algebraic growth harmonic functions are polynomials. So this is another type of Newell, theorem. So these are called Newell type of theorems. So in this talk, I will talk about the nonlinear version of a Newell type. So we want to classify nonlinear equations. So think about is Laplace U plus some nonlinearity equals 0, okay? And so we want to ask, are all solutions constants? For example, U equals 0 or U equals constant. These we call the Newell type theorems, right? And another question is, are all solutions rigidly symmetric? And this is called Gauss-Nienberg type theorems, right? This is Gauss-Nienberg in 1978 proved in a large class of solutions, the solutions are rigidly symmetric. So another type of question is, are the solutions one dimensional? In other words, you only depend on one variable. And this I call it the Giorgi type questions. And this is the question I want to study today. So if the answer is yes, then we can reduce the nonlinear PDE to an ODE, okay? And then we can solve the ODE problem. So this is the question, simple-minded question we want to ask. And unfortunately, as you're going to see from my talk, this is quite non-trivial. This question is quite non-trivial. So I will report some progress toward this type of questions on the Allen-Cahn equation today. So let's first look at the one-dimensional problem. So the one-dimensional problem, we can write on the solution explicitly, which is just using the ODE argument. And so this is a solution that connecting -1 and to +1. The connecting -1 to +1. So it goes when x goes to -infinity, goes to -1, goes to +infinity, goes to +1. And in between, so you have some kind of interface, right? In this case, the nodal set is just a point, okay? Because it's one dimension. So, but in this talk, we're going to use this function. So we're going to assume n greater than 2. So I'm going to give like 8 kind of classification results for this Allen-Cahn equation. I start with the so-called Giorgi conjecture monotone solutions. Then I will go to the so-called global minimizers, and then stable solutions, And the finite Morse index solutions R2 and R3, and stable solutions in high dimensions, saddle solutions, and finally half space theorems and the Toda system and the C to alpha estimate. So all these classifications, these 8 classifications are just we're trying to understand the solution structure of this simple equation. All right, so let me start with the classical Giorgi conjecture, which is the title of my talk today. So Giorgi in 1978 proposed this conjecture. And if U is a bounded solution of the Allen-Cahn, okay, which is a monotone in one direction. Say we know that U is, say, monotone in the last fiber, for example, okay, just monotone in one direction. Then the conjecture says at least when n less than 8, U is one dimensional. So now even in 1978, Giorgi already foresaw that there may be something wrong with this conjecture, when dimension is higher. And I will explain why, okay? And this dimension 8, Giorgi is one of the founders in minimum surface theory. So in minimum surface, and we know that when dimension n less than 8, all minimum graph are planes. And then for n greater than 9, there are non-trivial minimum graphs. So Giorgi, when he made this conjecture in 1978, he already knew that there may be some connection between this problem and the minimum surface. Okay, and that's why the dimension 8 appears. Okay, so the original Bernstein theorem with the minimum graphs are hyperplanes. This has been completely solved in the 60s by Giorgi, Fleming, and Simons, and then Bombardier and Giorgi and okay, yeah, just. So what is the Giorgi conjecture says that if you assume your solution is monotone in one direction, then your solution should be one dimensional. Okay, and it only depends on one variable, which means you can write down the solution explicitly, which should be the one-dimensional solution, right? Like this. Okay, and this is the one-dimensional solution. So this is the Giorgi conjecture. So the Giorgi conjecture has now it's 40 years ago. Now 20 years ago, the Gussup and Gray and made the first fundamental step in proving the Giorgi conjecture in dimension 2. And then 2 years later, Ambrosio and Cabre proved dimension 3 Giorgi conjecture. And then almost 10 years later, Savin and proved the Giorgi conjecture for dimension 4 to 8 under this actual condition, limit condition. We know that U is monotone in one variable. So as n goes to infinity, xn goes to infinity, it must have a limit. And so the actual condition is the limit is trivial, is a plus or minus 1. And this seems to have a natural condition, but still this is an additional limited condition. And then 2 years later, with Depino and Mike Krosik, we gave a counterexample to this. We prove that we prove that n greater than 9, there are solutions, okay, to the Allen-Cahn equation, which are not one dimensional and which are monotone, okay. equation in one variable. So this is sort of, this gives a complete answer to the Giorgi conjecture in large dimensions. So this is the first classification result. And it's almost done except 4 to 8 with this additional assumption. The second classification result is about the global minimizers. So this is a more energy, from the energy point of view, this is more physical, okay? This condition is more physical. So we see that U is a global minimizer of the energy functional. If you fix a domain and you fix your boundary data U, and you perturb inside, and U has the minimum energy. So this is a very natural condition, right? Global minimizer, in terms of energy point. Okay, so Savin in the 2009 paper proved that if U is a global minimizer, then necessarily U is one-dimensional, but for n less than equal to 7, not 8, n less than equal to 7. And 8 years later, with Yung Liu and Kenny Wang, we proved that Savin's conjecture, Savin's result is optimal. So when n going to 8, we have an example of a global minimizer which are not one-dimensional. So in terms of global minimizer, we have a complete classification, and there's no extra condition. So n less than 7 is true, n going to 8 and not true. And this is the complete classification result for Allen-Cahn equation. Okay, so if there are any questions, please send me on the chat or ask me, and I will be happy to answer any question.
Sorry, can I ask a question?
Yeah.
Yeah, I think I missed maybe the definition. When you say U is one-dimensional, do you mean rotation is symmetric?
Oh yeah. Up to rotation and the translation, I should say this. Yeah. Because this rigid motion in the for the equation. Okay, thank you. Yeah. All right, so let me go to the third classification, stable solutions. Now, the difference, the global minimizer implies stable, but global minimizer is a global stable condition. It's a global minimizer, okay? And the stable condition, stable solution is just a local, it's just a local condition, okay? So it's a spectrum condition, means your solution is locally stable. It's a local minimizer, may not be a global minimizer. Okay? So this is a spectrum condition. And so naturally we expect that for n less than 7, all stable solutions should be one-dimensional. And this is a conjecture, but this is only proof in dimension 2. And in dimension greater than 8, we have a counterexample. So in between 3 and 7 and 8, 3, 4, 5, 7 is completely open. And so one expects that dimension 3 should be true because for the minimum surface, we know that the stable minimum surface in dimension 3 are necessarily hyperplanes. And this is a classical result by Dokama, Pan, and Fisher, Cabre, and Schoen. And of course, for the stable minimum surface is open dimension 4 and 7. So let me just mention a very interesting result, recent result by Fagani and Sarah in 2019, and it's quite interesting. And they prove that the stable solution conjecture is true in R3, not for Laplace, but for half Laplace. So if you replace the Laplace by square root Laplace and use the same Allen-Cahn equation, then the all stable solution in 3 dimensions are 1-dimensional. And this is, I think, a quite interesting result. It shows, I think, the original stable solution conjecture should be true, but this is still a big open question. And I think if some young people come up with some good idea to solve this problem, maybe in the next 10 years, I hope so. Yeah. All right, so now, so we have done the monotone solution and global minimizer and stable solution. So next, we want to look at the finite Morse index solutions. So what are the finite Morse index solutions? So these are solutions that are not too unstable. So in other words, the Morse index, okay, which is the number of negative eigenvalues for this linearized operator, are finite. So these are the finite Morse index solutions. Now, mathematically, it means that it's stable outside a compact region. Okay, these two are equivalent. Okay, so you have a stability outside a compact region. So you don't know anything about the solution in a compact set. Okay, but outside the compact set, your solution is stable. So this is a finite Morse index solution. So in general, classifying stable or finite Morse index solution is a difficult problem in high dimensions. So let us just concentrate on the lowest dimension and the 2. Okay? The first classification of finite Morse index solution was given by Wang and myself, and in 2019, and we proved the following result. A finite Morse index solution in Allen-Cahn, okay, in 2 dimension Allen-Cahn, must have only finite many ends. So what does this mean? So a solution U of Allen-Cahn equation is called a multiple end solution, finite end solution. If outside a big ball, okay, inside a big, in compact set, we don't know nothing about the solution. But outside the big ball, the nodal set, this is the set where U equals 0, is asymptotically like some half lines, okay, straight lines. So you think about, it's like a big ball, outside big ball, you have some spikes, okay, some straight lines. So your solution goes from -1 +1 and just jump along this straight lines at infinity. So, and by just simple counting, the number of these straight lines must be even because you go from -1 to +1. So, and the set of 2n ended solutions called M2n. I call it M2n. So our result, classification result, says a finite Morse index solution must have only finite number of ends. So this is just one step toward classification of finite Morse index solution R2. So now we only need to study finite entity solutions. Right? Let's look at some examples of finite entity solution. For example, let's go 4n. Okay, first. Okay, the 4n solution is this proved by Dan 5 and Piantieri in 92. That we call it saddle solutions. So these are solutions that you divide R2 by in 4 quadrants. Okay, so U is 0 here in the x-axis and 0 on the y-axis, and the positive, negative, positive, negative. So you just simply by reflection, right? So this is a we call a saddle solution. Okay, this one has a 4n. You know, far away you said that this 1 and the 2 and the 3 and the 4. So you have 4 ends This is a four-ended solution. And you can generalize this construction, right? And to 2n, okay, with some dihedral symmetry. And so this is called a pizza solution. So you just divide the R2 into pizza, and you get a solution which changes sign, plus minus u equals 0 on this lines. So this, for example, this is the six-ended solution. So there's another type of finite-ended solution, which are given by the so-called Toda system. And this was just constructed by Depino, Krasik, Frank Packard, and myself in 2010. And what we prove is that if you have a solution to the Toda system, okay, then you can construct a solution to the Allen-Cahn in 2 dimensions, whose nodal set are governed by the Toda system. So it's very interesting. It seems says this is the first time you say that Toda system is embedded in the Allen-Cahn equation. Now, such a simple equation, Allen-Cahn, okay, and inside you see a Toda system, and the Toda system is embedded in this Allen-Cahn equation, and this is this is what we discovered. So, for example, if you take so this is like a 10-ended solution, right? You have 1, 2, 3, 4, 5. These are 5 curves, and they satisfy the so-called Toda system. And then you have a solution goes from -1, +1, -1, +1, and -1, +1. So you look at the cross section, and this is what you see. Your solution look like this, change sign. And this is like your nodal set. So the nodal set are governed by the Toda system. So this is another kind of finite-ended solutions. Okay, question. Can we have a complete classification of these 2n-ended solutions? Are solutions, the set of solutions, okay, to the 2n-ended solutions, are they connected? Okay. So what is, if they're connected, okay, what is the dimension of this manifold? Okay. And what is the Morse index? Right? We know that final Morse index solutions are finite end, right? So if I have a finite end, can we compute the Morse index, right? And all these questions are completely open for Allen-Cahn. The only partial result is 4, M4, which is 4-ended solution. And what we can prove is the set of 4-ended solutions is connected. Only the first question is answered. The 4-ended solution is connected. And so you can have a connected family of solution which go from the Toda solution to the Toda solution. And this is first proof by Krasik, Liu, and Packard in 2014, and Gui and Liu and myself in 2017. We used the mountain path characterization to construct such solutions. Okay, so it seems that for the Allen-Cahn equation, it's difficult to give a complete classification of 2n-ended solutions. And so we will ask, what about the other nonlinearities, the other double Worth potential? So for example, we take a double Worth potential like 1 plus cosine u. So the equation will be like this. Okay, this is called the Sine-Gordon equation, called the elliptical Sine-Gordon equation. And this is a double Worth potential, okay? And for this equation, you can write down the 4-ended set of solution explicitly, right? And okay, and this is a complete, this is explicit solution. And in fact, you can write down all two-ended solutions. Okay, all finite-ended solutions can be written down explicitly, and they are given by this parameterization, by this these are solutions of two-ended solutions. They are given by like 4 times tangent inverse gn over fn minus pi, and the fn is like this, and the gn is like this, and we prove that these are all two-ended solutions can be written in this form. Okay, this is a joint work with Yong Liu. So you can write down all two-ended solutions for this problem. And with this information, and we can now give a complete classification of two-ended solutions for this nonlinearity, which is Sine-Gordon. And we show that this is a 2n smooth and connected manifold, and each solution is non-degenerate. So you have kernel is 2n dimensional, and we can compute the Morse index explicitly, okay, with n times n minus 1 over 2. And now for the original Allen-Cahn equation, we have a lower bound for the Morse index, and this is given by Montone. The lower bound for Morse index is n minus 1 over 2. So this is, of course, you see a big gap between n minus 1 and n times n minus 1 over 2, because this is like n square order, and this is just the linear order. But even this is, the proof is quite complicated. So there's a big gap here. And for the Allen-Cahn equation, and is completely open, but for the Sine-Gordon is completely solved. Okay, we have a complete classification of 2n finite-ended solutions. So we have a complete classification of finite Morse index solutions. So this is the third. This is the fourth classification result. So the main the idea of a proof is the inverse scattering, and we can write down, we can find the so-called Lax-pair for the unique Sine-Gordon, and then using the Lax-pair and the double transform, we can find all solutions, and then use the inverse scattering. We can compute, we can prove the non-degeneracy. Okay, and so this is the fourth type of a classification result. Are there any questions so far?
Actually, I have one.
Yeah.
So when you say the bounded Morse index implies bounded ends, right?
Yeah.
We have like a quantitatively relation between them.
Oh, yeah, this is a very interesting question. I understand if you are from differential geometry,
Yes.
and you know that there are some quantitative, that if find an end, if you find an end, you can estimate the Morse index, right?
Yes.
Okay. Yeah, you have a lower bound for the Morse index. Okay.
Yes, by the ends, I think in
At the
theorem.
end. But here we know. Here the only result is this result by Montone, right?
Okay.
Right? n minus 1. And he followed the differential geometry approach. Okay.
Okay.
Right? And he get n minus 1. But you see that this is not optimal. This is n, right? We should get n square order. So there's a big gap here. I don't know what I think this is a quite interesting problem, even to show, the lower bound should be n square order, right? Should be, this is a very interesting question. Yeah, yes.
Thank you.
Okay, so let me now go to the fifth classification is find the Morse index solution R3. Right? Let's look at the R3. So we have done find the Morse index R2. Let's go to find the Morse index in R3. Now you see that in R3 we cannot even classify the stable solution. Right? So even the stable solution is open, is largely open. Right? So what about the final Morse-integral solutions? Well, final Morse-integral solution, we have existence. Okay, the final Morse-integral solutions, and this is proved by the Pino, Krasik, and myself in 2013. So what we prove, if you have an embedded non-degenerate complete minimum surface with a finite total curvature, then you have a solution to the Allen-Cahn equation whose nodal set close to the scaling of the minimum surface. So in other words, it's like a minimum surface. Now, the most we can also prove, okay, the most integral solution of the U, the constructed U, equals the index of the minimum surface. So we have a direct one-to-one correspondence between the minimum surface in R3 and the complete embedded minimum surface in R3 and the finite Morse index solution in R2 in R3. So a particular example is the catenoid, which has 2n. Right, this is the catenoid with this is the first non-trivial minimum surface, which is a 2n. So the solution we construct, okay, arises from large catenoid. So you have to rescale the catenoid, okay, and the nodal set of the solution is asymptotically like z equals like 1 over epsilon log r. So it's a large catenoid. It's a large catenoid. On the other hand, with the Pino and Agudelo in 2016, we constructed another two-ended solution using Toda system. And for this two-ended solution, and this is like two disjoint, two leaves, like, okay, you put up like two hyperplanes using Toda system. And the angle between z and log r is like a square root of 2. Okay. So now we have two family of solutions, two-ended solutions. So a natural question is, do they connect? Yeah? And they should connect. You know, one is like a square root 2, another one is like a 1 over epsilon. Right? And this is a proof, and with Gui and Yungliu in 2017. And we prove for each k in between, square root 2 and plus infinity, there is such a solution with 2n, okay? And so the proof is quite complicated because we cannot do this nodal perturbation result. So this is based on modular space theory and the bifurcation of real analytic varieties. And this is not a perturbation result. So the classification of finite-ended solution in R3 is largely open, right? And the only known result is in high dimensions, okay, n greater than 4. The only known result is axially symmetric case. Right? In the axially symmetric case, with Gui and Wang, and we prove that this is a similar result like in 2D. In between 4 and 10, all finite Morse solution must depend on z only. Okay. For n equals 3, we can prove the finite Morse solution has the finite energy, so like a finite end. Okay, and for n equals 3, the Morse one solution has 2n. But so this is the result for in the axial symmetry case. Now, without axial symmetry, this is a completely open question, and this is a very difficult question. Okay, so now let me turn to classification, the sixth classification result, the stability of saddle solutions. So as I said before, with dimension 4 or higher, there are very few classification results, and even the existence of a solution is quite difficult. So let's first look at the following question. What is the generalization of the saddle solution in R2? And to high dimension. So this is the set solution constructed by Dan, 5 and Pelletier. So you divide the x-axis and the y-axis. You divide the region into 4 parts, and 1 part positive and negative, positive and negative. And this is the set of solutions. So the nodal set are just 2 axes. So what should be the natural eigenvalue of the set of solution in high dimension? What happened? Just one moment. Okay. Just one moment. Okay. Okay, so maybe my computer frozen. Okay. So the natural eigenvalue in high dimension is also called Simon's cone. So what is Simon's cone? So Simon's cone is you take R²m, you look at the first m radial coordinate, and you look at the last m radial coordinate, and the Simon's cone is a cone so that the first m radial coordinate equals the last m radial coordinate. So if we introduce 2 radial coordinates s and t, then the solution, if we look for solution which is axially symmetric in s and axially symmetric in t, and then this will become just a 2-dimensional problem. So what is settled solution? So settled solution is a solution that when you switch s and t, and the solution will get a minus sign. So otherwise, your solution vanishes exactly on the so-called Simon's cone. So the existence and the uniqueness of this settled solution are proved by Cabre-Terra in 2010. And so the settled solution is this is the S fiber and this is T fiber. So the solution is positive for S greater than T, negative for S less than T, and equals 0 for S equal T. And this is the Simon's cone. Okay, this is the so-called Simon's cone. So Cabre in 2012 proved the settled solutions are stable in dimension 14 or higher. Remember, this is a 2m, right? M greater than 7, so dimension is 14 or higher. And unstable for dimension 6 or lower. So the Morse index is infinite when in dimension 4 and 6. The Morse index equals 1 in dimension 2. Okay, this is the Schatzmann's result. So in this paper, they conjecture that the settled solution is also stable in the remaining 3 dimensions, 8, 10, and 12. Okay, 8, 10, and 12. And this was solved. We solved this with Yongliu and Kene Wang. And we proved that the Cabre-Terra solution are stable in dimensions in the remaining dimensions. So this gives a complete classification, the stability of the settled solutions, okay, in all dimensions. And this is quite a long proof, very long proof. I will not, I just give you some main idea of the proof. And we need some quantitative point-wise estimate of the settled solution. Okay, for example, one of the main estimate we have in the paper is to estimate the derivative, the second order derivative by u under the first order derivative. And this take quite a few pages just to prove this point-wise estimate. Okay, so in the remaining part, I will talk about the last 2 classification results, the half space theorem and C2 alpha estimate. But before we do this, any questions? so far? Any remarks? Okay, so in the last two classifications, last two results consider the general property of the solutions, right? So far we have classified monotone solutions, stable solutions, global minimizer, stable solutions, finite Morse index solutions, and this okay, finite endless solutions. So in the last two result, we were concerned with the general property of the solutions. Okay, so the first classification result is called half space. So in minimum surface theory, Hoffman and Mix in 1990 proved so-called weak half-space theorem. And the theorem says if you have a connected proper non-planar minimum surface in R3, and if it's contained in a half space, okay, in a above a plane, then it must be a plane. So this is a so-called weak half-space theorem. So, and this strong half-space theorem says if I have two minimum surface, one is above the other, then there must be parallel planes. Okay, so if you have two minimum surface and if they are not planar, and then they must intersect. Okay, so this is called a strong half-space theorem. So using this half-space theorem, the Hoffman Mix half-space theorem, Coding and Minkowski in 2008 proved the so-called Yale's conjecture. So the plane is the only complete embedded minimum disk in R3, and so the half-space theorem is very important in minimum surface theory. So we want to ask, are there half-space theorems for Allen-Cahn equation? And this is this is true, and this is this result from last year. So this is a joint work with Francis Hamel, Yong Liu, and Scarpati and Kenny Wang, and we appeared last year in Korea. So what we prove is yes, we have half-space theorem, and if dimension n less equal to 3. Okay, if n less equal to 3, and if we have a non-constant solution to the Allen-Cahn equation, and suppose the nodal set is contained in a half space, then U is one dimension. So after some rotation and the translation, U can be written like a one-dimensional function of a one variable, okay, function of a one variable. So this is the weak half-space theorem, and we also have a strong half-space theorem, but the strong half-space theorem we can only prove in R2, not in high dimension, not in R3, and the reason is let me just give you a sketch of the proof, which is quite easy. Once you have the weak half-space theorem, if you have a stable solution, right? If you have two solutions, one above the other, U2 greater than U1, then you can construct a stable solution in between by sub and shift solution method. And now all stable solutions R2 are one-dimensional. So as a result, all the half space is one-dimensional. So then the nodal set for U2 is contained in a half space, and then this is a proof. Okay, this so then you must be one dimension. So both must be one dimension. So for greater than 3 is completely open. Let me just show why we need a dimension 3. And the proof is completely independent from geometry. We don't use any geometry, okay? So in the Hoffman-Mix theorem, proof they use Weierstrass representation. This is a very important, characterization of a minimum surface in R3. And but here we don't have this kind of Weierstrass representation. We don't know anything about the nodal set, right? The nodal set can be anything. The nodal set can do anything. Okay, can be unbounded or take some times. Okay, and it's not a minimum surface. Okay, we don't know. Okay, so what we use is a so-called Parsev type identity. I think this is this is the only case where we use the Parsev identity to prove a one-dimensional result. This is quite an interesting application. So let's consider dimension 3 case. Suppose we have a solution to the Allen-Cahn equation, and then we have suppose we have bounded domain like omega, and then we have the so-called Parsev identity. And so this is a Parsev identity. So this is the energy, right? This is the bistable. This is the double Wall potential, and then we have gradient u dot x and gradient dot mu. Okay, so this is the equation we're going to use. Okay, we want to use this to prove the one-dimensional result. So how do we prove the one-dimensional result? We work in this space. Remember, our nodal set is above x equals 0. Okay, so nodal set is here, and for the nodal set, we know nothing about this nodal set. Okay, we just know it's above x equals 0. Okay, but we know nothing about the nodal set. You may be disconnected, may do anything. Okay, right? So what we work? We're working on this part of the domain. Now, on this part of the domain, on the part where x is negative, on this part of the domain, we know u has a fixed sign. So, for example, let's say u is like negative. Okay, we can assume u is negative on this side. If u is negative, then we know that u must go to -1 at infinity, and this is easy to prove. Okay, you go to -1. So at the infinity, we know u is like a -1. Okay, so now let's use the Parsev identity and on this set, on this cylinder. Okay, in this cylinder. So what do we use? So we use Parsev identity on this in this cylinder. So on this part, on the bottom part, we take x is okay. We take x is like 0, 0, 1. So on the bottom part, we get this identity. Okay, we get this quantity. Now on the vertical part, this is 0. So we only get the derivative. Okay. So we have so if we look at this, the antiderivative of this guy, let's call it f, and we have this trivial identity, Parsev identity, which is f prime of s equals g of s of s. Now, if we play with this identity, okay, it's important. So in the high dimension case, this will be s to the m-1, okay, m-2, sorry, m-2. So if we play with this equality here, now remember that 1 over s is not integrable. 1 over s is barely when we integrate 1 over s, you get a log s. So if we play with this inequality, the equality, and we'll get the proof. We get the rigidity result. Right? This you play with, you get some kind of ground hole inequality. Play with this inequality. So this is a quite an interesting proof, because this is the only one we only use the we don't use any property of the nodal set. Okay, we just the only result, the only tool we use is the Parsev identity, and from this Parsev identity we get the rigidity result, the one-dimensional result. So this is the proof of the half space theorem. Okay. Okay. Any questions? Any remarks? I'll go to the last one. Okay, so the last result is a quantitative result of general solutions. Okay, so I'm going to discuss the so-called the role of the Toda system in the uniform C2 alpha estimate for interfaces for stable solutions. So this is the question we want to answer. Suppose U is a sequence of stable solutions to the Allen-Cahn, and suppose the nodal set is uniformly C1 alpha. Okay. Now, this has been proven for stable solutions in some dimensions. Okay, this has been so the question is, can we get uniform C2 alpha estimates? So how to go from C1 alpha and to C2 alpha? Okay, from suppose we already have the C1 alpha estimate. Can we get to the C2 alpha estimate? And this is the result I obtained with Kenny Wang 2 years ago. And we show that yes, okay, but in lower dimensions. Okay, so our result says if you have a sequence of stable solutions on Allen-Cahn, so in a ball, unit ball, okay, so that's in a bounded region. Let's assume that the nodal set is uniformly C1 beta, C1 alpha. Okay, so this is our assumption. Okay? And then if dimension n is equal to 10, then we have C2 alpha estimate. And moreover, we have the mean curvature. We can prove the mean curvature is of this order. Right? So you see that from C1 alpha to C2 alpha, we need a dimension restriction, which is n less equal to 10. Okay. And why do we need this dimension? So before I do this, now let's discuss the multiplicity one case. Right. So if we have Allen-Cahn equation and convergence, we have the so-called convergence of the energy functional, and this is proved by Tanegara and Masakura and Garako in 2018 also. So if we consider multiplicity one case, in the multiplicity one, so each okay, so means at each place you only have one interface. Okay, so you don't have multiple interface connection. So, and we prove that if multiplicity one case, we have C1, we have C2 alpha. Okay, and this answers a question by Tanegara in 2010, and this is conjectured in his paper. Okay, and so if a multiplicity one case, we can always get from C1 alpha to C2 alpha. Okay, now how to get a C1 alpha? You can show me your graph, your nodal set is Lipschitz or flight, then you get a C1 alpha. Okay. So we prove this C2 estimate in dimension 2 first, and then we use this C2 alpha estimate to give a classification of a finite Morse index to finite end. Okay, finite Morse index implies finite end in dimension 2. And the Giorgi and the Mantonidis, they extended this estimate to dimension 3. And then with this estimate, they can prove the multiplicity one conjecture by Marcus and Neves. And so they use this estimate and to construct a Jacobi field, okay, and a positive Jacobi field. And this is a very interesting construction. All right, so in this theorem, the dimension 10 is optimal, okay? And so when dimension 11 or higher, with R² and the Pino, and we have a counterexample. So what is the counterexample? So in dimension 10, if you look at the Newell equation, which is like two-component Toda system, and the Newell equation has a rigidly symmetric stable solution. And you can write on this stable solution. And then you can rescale this Newell, okay, the solution to the Newell by this scaling, okay, and this form a foliation of R_n + 1. And then we use this foliation, okay, and then we can construct a solution to the Allen-Cahn, okay, and this solution turns out to be stable. And then if we rescale the solution we constructed from this using this Newell, and then we compute the nodal set. So the nodal set is given by this Newell, and you found that the nodal set, the nodal graph is C2, but not C2 alpha. Okay, so it's C2, but not C2 alpha. So so from C1 beta to C2 alpha to C2 alpha, and it's no longer true in dimension 11 or higher. Okay, so maybe in the last few minutes, maybe just give you a sketch of the proof of the C2 alphas. And what I want to stress here is the role of the Toda system played in this in this theorem. Okay. So what is the main difficulty in proving this this theorem? Okay, the C2 alphas. The main difficulty is that the interfaces, you have lots of interfaces, they will collapse to each other. Okay, all these interfaces, they collapse to each other. Okay, if and you don't know, we don't know if the multiplicity, we finite multiplicity, we have no idea. Okay, whether or not it's a finite multiplicity. So how do we exclude this case? Many interfaces, they collapse to each other. So this, and since we have C1 bond, so we get a C2 bond, and then we have locally all these interfaces can be represented by graphs like this graphs, and then we prove this. We prove that the interfaces, they interact with each other. And how does what is the interaction equation? And this is the interaction equation. We found that the interfaces, they interact by this formula, right? This is the mean curvature, and this is exponential interaction between neighboring interfaces, leaves. Okay, so we prove this by a reverse infinite dimensional reduction. This was developed by the Pino and myself, but here we use the reverse order, this reduction. Okay, so once we have this, then we're going to say that what is the obstruction of the C2 alpha estimate. So the equation can be approximated because we have a C1 alpha estimate. So equation can be approximated like this. Now you see that if these two leaves, if they are far, okay, then this will be very small. Okay, then we get a C2 alpha. So the problem is if this one of the two leaves, they stay close, like epsilon, like a square root over 2 epsilon log epsilon order, and then we plot, okay, at this level set, okay, at this graph, and what we see is an entire solution of the Toda system in the lower dimension in R_n - 1. So what we prove is the obstruction of the C2 alpha convergence. Right? What is the obstruction? The obstruction is the total system. And this is precisely the reason. That's why if you have infinite many of this, you have these interfaces that collapse each other. Why do they collapse each other? Because there's a total system in between them. The total system is the main reason, okay, for this collapsing. So this is the what we prove. No, now with this result, so the obstruction of the C2 alpha estimate convergence is the total system. So with this result, then we can use the stability, okay, to of the solution U, reduce the stability of solution to stability of the total system. Okay. So in conclusion, the uniform C2 alpha estimate of class-term interface does not hold, implies the existence of entire stable solution of the total system. Okay, so then we need to prove a Newell type theorem for the total system. The no stable solution of the total system in Rn-1 for n less than equal to 10. Okay, and how to prove this? I will prove this by so-called Epsilon regularity theorem. So if we have n less than equal to 10, and if we have a stable solution to the total system, then we can have a uniform bound, L1 bound on the L1 uniform L1 bound on the forces. Okay. Now, so if you have a uniform L1 bound, then you can have point-wise, okay, lower bound on the distance, okay, between these two leaves. And so with this bound, then you can show that you get some decay. You show that you get some decay estimate, and then you show that this is impossible. Okay, so so this is the last classification result. We use the total system, okay, and to prove the C2 alpha estimate. And so finally, let me summarize what we have discussed today. I discussed 8 types of classification result for the Allen-Cahn equation. And we go from monotone solution to global minimizer to stable solution, final Morse index solution, and then saddle solution, and then half space theorem, and then the C2 alpha estimates. And you see that such a simple equation, which is so simple, which is, let me just recast, is minus alpha u equals u minus u cube. Such a simple equation, and it contains very rich, okay, mathematics, right? You have minimum surface, you have a minimum integrable system, okay, and then you have the total system, and so it has and furthermore, this, as I discussed from the beginning, the Allen-Cahn equation, or in general, the bicycle equation, is like the prototype, is the founding equations for studying interfaces in mathematical biology, phase transitions in physics, and also the defects for superconductivity. So such a simple equation has many applications in applied science, in physics, and then this rich mathematics. I think this is this is quite an interesting question. I hope my talk will give you a survey on what we have done so far. I hope you are interested, and thank you for your attention.
Thank you very much, Dr. Wei. I forgot to mention, Dr. Wei is also the recipient of Jeffrey Williams Award, and this was the prize lecture that was supposed to be presented at the summer meeting in 2020. Unfortunately, because of the pandemic, it got postponed. But we have an opportunity, maybe because of the pandemic, to be able to attend your lecture from many parts of Canada. Thank you very much. If I see that there's a question in the chat. If you're, but I'm not a math person, I would let you read that.
Okay, so let me, yeah, okay. Question, in your paper one way, you assume the BU is bounded. This is uniform C11 regularity. How do you go from C1 beta to C11? Okay. Okay. So okay. This is a very interesting question. And okay. And we assume the C2 bound, okay? We assume the C1 one bound, and by the scaling, okay? So, and we use the BU, okay, which is, we use the B of U, which is the C2, as a scaling parameter. This is a scaling parameter. So by scaling, and then we can assume the BU is 1, okay? So first of all, we have the BU goes to 0. This is what we prove, okay? BU goes, and then B of U is sort of like the scaling parameter. So we use B of U as a scaling parameter. And so by rescale, you assume that the C2 is a bound.
Does this I guess answer your question? The person who yes, I guess.
Yeah.
Are there any more questions?
I have a general question.
Yeah.
It seems like what you were talking about, it seems like a parallel a theory of minimal surface theory, Allen-Cahn equations, right? So, and you said it related to minimal surface theory. So I'm wondering, does that mean that the nodal set of the solution of Allen-Cahn equation is actually a smooth minimal surface? Am I right?
Okay. This is a great question. What I want to emphasize is that, okay, this is just a deception, right? Allen-Cahn is not a minimum surface, okay? Allen-Cahn equation is, in some sense, is more difficult than minimum surface because it is not a minimum surface. The nodal set is not a minimum surface.
Not a
Only
minimum
in some
surface.
limit is a minimum surface. So, and that's the main reason that we cannot use all the minimum surface theory is precisely it is not a minimum surface.
Okay. So you don't have any geometric interpretation of the nodal set. So you can't use
no, we cannot. That's the main reason. That's why we cannot use, like for example, Wasser's representation, right? We cannot use Simon's algebra. We cannot use this kind of things in the minimum surface to do Allen-Cahn. Like the half space theorem, we cannot use the Wasser's representation.
But do we know it's a smooth submanifold? Do we know that?
No, because you may have some course. Yeah, you only know because by Sato theorem, you know that it's smooth everywhere except some finite number of points. Yeah.
Oh, okay.
Yeah. But you don't know anything about the mean curvature of the equation of the nodal set. No, nothing. Yeah, yeah.
So only when the epsilon goes to 0, it
only
converges.
when you look really deep on and you assume the energy is bounded, then yes, it is like, yeah.
Okay, I see. Okay. Thank you.
Okay, follow-up question. Do you use C1 beta regularity just to see BU decay to 0? Yes, exactly. Yeah. The answer is yes. Yeah. So all the papers are on my website. I encourage, if you are interested, go to my website, download the papers, and if you have any questions, send me an email. I'll be very happy to answer. Yeah. You are muted.
Sorry,
Sorry.
this
Yeah.
is also recorded, so I
Yeah.
can send you the recording of this lecture, and then in that email I can include Dr. Wei's website too, so they can.
Okay. Okay. Yeah. Yeah. Okay. Okay.
All right.
All right. Okay. Yeah.
If there are no more questions, thank you so much, Dr. Wei, and thank you everyone for attending this webinar. We hope to see you at the virtual meeting this summer at U Ottawa, and we hope that this pandemic is over soon too.
Yeah. Okay. Yeah.
All right.
Yeah. Okay.
Bye.
Bye.
Bye-bye.
Okay. Bye.